Welcome to this tutorial on design and analysis of Bandgap Reference Circuit, BGR. In this lab, our objective is to design and simulate different BGR configurations, measure their performance, and compare their figures of merit. But before we begin the design, let's first take a brief look at what a BGR is and why it plays a critical role in analog circuits. Analog circuits need stable DC references for consistent performance. BGR circuits provide this stability across supply, process, and temperature variations. Commonly used in biasing, op-amps, ADCs, and DACs. In this lab, we will design a basic BGR circuit and simulate and compare PTAT and CTAT behaviors. Now that we understand the importance of BGR and analog IC design, let's define the objective of this lab. This lab focuses on designing and simulating BGR circuits using a schematic editor with PDKs like TSMC65, TSMC13, TSMC18, or GPDK18. We'll start with an ideal BGR design to calculate PTAT and CTAT. Then, we'll simulate the transistor level implementation using those values. Finally, we'll compare results from both ideal and practical circuits. Let's start by understanding the theory behind the BGR circuit before moving on to the actual design. A bandgap reference circuit merges CTAT and PTAT components, which respond oppositely to temperature changes. Proper tuning of specific constants allows these effects to cancel out, producing a temperature-independent reference voltage. The resulting balance is shown in the figure. Let's take a look at the basic CTAT design. Current through a diode is given by this equation. I0 equals to Is multiplied by exponential of Vd over Vt. Let's call it equation 1, where I0 is current through the diode. Is is reverse saturation current. Vd is voltage across the diode. Vt is thermal voltage. By writing equation 1 in terms of Vd, we get the second equation. From this second equation, we can say that the current through the diode is highly dependent on temperature. As the temperature increases, the voltage Vd decreases, resulting in a complementary-to-absolute-temperature (CTAT) behavior. Now we shall take a look at the PTAT design. From the figure on the screen, Vd1 is given in equation 2. Vd1 equals Vt multiplied by natural log of I0 by N times Is. Now we can form the PTAT equation by subtracting equation 2 from equation 1, which will result in PTAT equals to Vd minus Vd1, which is equal to Vt multiplied by natural log of N, where N is the number of diodes. Hence for PTAT, Vt is directly proportional to absolute temperature. Now consider this figure in which a resistor is connected in the circuit. If same current flows through the branch, we will have current I0 equals to Vt over R1 multiplied by natural log of N. Let's call this equation 4. If we route this current through a separate PTAT with resistance R2, then the voltage across that resistor will be Vr2 equals to Vt multiplied by natural log of N multiplied by R2 and divided by R1. Now that we have understood the concept behind BGR and how to develop a reference voltage based on a CTAT and a PTAT, we will move on towards designing BGR in Cadence Virtuoso. To start designing the BGR, first create a new library and give it a meaningful name, such as analog_IC_lab_7. Then, create a new cell view inside this library with the name CTAT. Once the schematic for CTAT is opened, create the CTAT circuit as follows. Place a PNP transistor, an ideal current source, IDC, and two ideal voltage sources, one for VDD and one for VSS. After placing all components in the schematic, wire them up and add labels to the wires. In the Edit Object Properties window of the voltage and current sources, type VDD and ID, respectively. Next, check and save the circuit, and fix any errors that appear. Now go to Launch and open ADE Explorer. Make sure all design variables are copied. Set ID to 5 micro and VDD to 1.2 volts. In Analyses, select DC, and under Sweep Variable, choose Temperature. Set the start value to -40 and the stop value to 125. Then go to Outputs. Select the CTAT node from the schematic to be plotted, and press the green play icon to start the simulation. Once the simulation is complete, the CTAT waveform will be displayed. The waveform displayed is exactly like that of a typical CTAT, complementary-to-absolute-temperature, meaning it should decrease as the temperature increases. This marks the end of the CTAT design. Now, we will move on to designing the PTAT circuit. To design PTAT, create a new cell view in the same library and name this cell view as PTAT. The first branch of the circuit will be the same as previously made for CTAT. We can either copy this branch from the CTAT cell view by using shortcut key C4 copy, or we can create this branch again. In this tutorial we shall copy this branch from CTAT cell view. The only difference is that here we will name output node as VD instead of CTAT. Now, to create the PTAT branch, place two PNP transistors in parallel configuration and place an ideal current source to drive the current through the transistors. Go to Edit Object Properties of the transistors in parallel and change the multipliers from 1 to 4. In this way the value of N will be 8. We have set the value to 8 for better matching. Label the output node of this branch as VD1. Label the ground wire as VSS. Now check and save and clear any errors. Next go to Launch, then click on ADE Explorer. In the same way as done for CTAT, set ID as 5 microamperes and VDD to be 1.2 volts. In Analyses, select DC, sweep variable to be temperature and start and stop values to be -40 and 125 respectively. From Outputs, select node VD and VD1 to be plotted. Then click on green play button to start the simulation. Waves of both VD and VD1 will be displayed. We need to make sure that VD and VD1 are as close to each other as they can be. Now change the circuit by connecting a resistor after the current source. This resistor is R1 from equation 4. In equation 4 all the variables are known, like current I0 is known, VT is known and N is also known, hence, we can calculate R1. After calculation, the value of R1 comes out to be 10.813 kiloohms. Go to Edit Object Properties and change this resistor value to be 10.813 kiloohms. Now before simulating this circuit, label the output node as V2. Now go to ADE Explorer, in Outputs select V2 to be plotted along with VD. Now, click the green play button icon to start the simulation. In this simulation the resultant waves, VD and VD1, are more close to each other as compared to previous simulation. Next, we shall employ the current mirror technique instead of ideal current sources to drive the current through the transistor and ensure that both currents are equal. Now, we shall use current mirror instead of ideal current source. To do this, first remove ideal current source from both branches. Instead of the typical current mirror topology, here we shall use the self-biased current mirror topology. The reason for using this topology is that it is independent of the supply voltage VDD. To make the self-biased current mirror, first place two NMOS transistors, and connect their gates together. Then, connect the gate and drain of one of the transistors. Next, place two PMOS transistors, and wire them up as shown. Now connect the self-biased current mirror with the two branches as shown. Don't forget to connect the body connection of PMOS with VDD and NMOS with VSS. Before simulating this circuit, first we need to edit the aspect ratios of this current mirror. Make the width of all the transistors as 80 micro, length as 5 micro, fingers as 10 and multipliers as 10. Now check and save the schematic and clear errors if any. Now go to Launch and open the ADE Explorer. In the ADE Explorer, plot the current of the branches. To plot current, go to Outputs, then in Schematic select the drain terminals of both the NMOS transistors. Now hit the green play button to start the simulation. Waves of currents from both branches will be displayed. Now, as we discussed earlier in the PTAT theoretical background, we shall route the current of PTAT through another branch with resistance R2. To do that, place a PMOS transistor and connect its gate with the current mirror as shown. Next, connect the resistor R2 in series with the PMOS. The value of R2 can be calculated from equation 5. Label the output node of this branch as PTAT. Now, go back to ADE Explorer and, in Outputs, select the PTAT node to be plotted. Run the simulation by clicking on the green play button. The PTAT wave will be displayed on the screen. Now we have to edit the circuit again and add both the CTAT voltage and the PTAT voltage. This will give us the required reference voltage. Now, to make the complete BGR circuit, create a new cell view named BGR. In the schematic of this cell view, copy the last PTAT circuit. Once the PTAT circuit is copied, we need to make some changes to it. What we need is to add CTAT and PTAT voltages together to get the desired reference voltage. To add voltages, they must be connected in series. Copy the CTAT branch and connect it after the resistor R2. Rename the PTAT node as VREF. Now, go to Launch and open ADE Explorer. This time, select Create New View. After ADE Explorer is open, first copy the design variables and set VDD to 1.2 volts. Then go to Analyses, select DC, choose Temperature, and enter -40 and 125 in the start and stop values, respectively. From the outputs, select VREF and CTAT to be plotted. Now, hit the green play button to run the simulation. The result will be the waveforms of VREF and CTAT. We have obtained the VREF and CTAT waveforms, but we also need to see the PTAT waveform. To obtain the PTAT waveform, subtract CTAT from VREF. This can be done using the calculator. Follow the steps as shown to get the PTAT waveform. First, open the calculator. Then, send both the waveforms to the calculator. Perform the subtraction operation and send the resultant waveform to ADE Explorer. Name this waveform as PTAT. Now, again run the simulation to see the result. From the waveforms of CTAT and PTAT, we can see that they are not equal. This mismatch occurs due to a slight mismatch of current in all the branches. Now, to make the currents equal, we shall change the resistance values. Change the resistance R2 value to 550 kiloohms. Next, plot again and observe the results. After changing the resistance values, both the CTAT and PTAT curves intersect at the midpoint. Since PTAT and CTAT compensate each other, we get a constant voltage, Vref, at the output. Also, this reference voltage is independent of temperature. This marks the end of the BGR lab tutorial. In summary, we developed the bandgap reference, or BGR, using CTAT and PTAT blocks. Instead of ideal current sources, we used current mirrors for realistic biasing. For the exercise, repeat the tutorial using a cascoded current mirror for improved current matching. Ensure that equal current flows in both branches and compare the results with this lab. Additionally, try designing the BGR using an operational amplifier and analyze its performance. Thank you for watching this tutorial.